Yes,
Did you want the poster PDF?
Yeah.
Sorry? Do you want my poster version in PDF?
Yes.
Do you have the pen drive?
Yes.
not the physical properties, but the transport.
So, oh,
Yes, there's also maybe
Related.
okay, it was very
I think it's not so highly scientific, maybe
Yeah, we had saw that you had not seen him in so we asked him to be a chair because the reason for some reason.
So we start the last session of today, and we will give the floor to Jirka to give a keynote lecture on on Hydrus.
He will give the floor to Diedrich after my presentation. Well, I have several technical things first. We have all your presentations obviously at this computer right now, and so I was thinking that I may convert them into PDF files and then put them on the website and link them to the, basically to the program as it is there. So if you have any objections against that, so please send me an email or simply delete it during the coffee break. Yeah, so it's going to be probably the simplest. So if you have any objections, I know that Rien, for example, cannot put his presentation there because he showed some things which shouldn't be there. Then obviously we don't have posters, we don't have files for your posters, so if you are interested in posting those, so send me a PDF file at that and I will post it as well. So that's the second thing. Then papers, yeah, for the proceedings. So we will prepare the proceedings. It's going to be only online, we will not print it, but we will still give it IPSN or whatever, the special number. Deadline obviously was yesterday, and, well, if I receive it within 2 weeks, it's going to be okay, yeah, but 2 weeks is about the maximum. We are planning to, well, first of all, I certainly want to get these papers in the format. I send you the template, so, and if it's not in that format, I will reject that. I'm not going to be formatting it for you, okay? So that's one thing. Second thing, we may look at some of that text and maybe briefly edit it. So if you object against that, send me an email also, yeah? So that's technical, I guess. And then I go now, and I hope that my clock starts ticking now. Well, so I prepared this presentation, and I spent this 1 hour lunch break just deleting the slides because they were shown by Günther or Diedrich already. So new features and developments in Hydrus software package. And so I will not show any applications of that. I simply discuss some of the new features which we implemented during the last few years. And first I would like to acknowledge my co-authors. So basically mainly Diedrich, who's the driving force behind the FreeC link, the Hydrus, Günther, who is the driving force behind those wetland modules, And then it's called Bradford, with whom I'm working very closely on the development model for particle transport and for colloid-facilitated transport and so on. Well, so obviously the platform for all this is Hydrus. And so the main thing which I want to, at least the first part of my presentation, is basically discuss some of these modules or add-on modules to the Hydrus code. And you see here the modules which are currently available. So you have heard a lot about FreakC. Then we have a module called CRide, which simulates particle transport and particle-facilitated solute transport. Then we have a module called UPerm, which focuses on preferential flow and solute transport. We have a module on SubChem, which simulates, in addition to flow, also carbon dioxide and measuring chemistry. Then obviously Wetland Module, and finally the Fumigant module. Well, FreakC, you have heard about it too, so I will skip these slides. I will just mention that most of you, or those who are using FreakC in Hydrus, are probably using it in Hydrus 1D. And in Hydrus 1D we have these text editors where you specify all the input into the code. And we have spent a lot of time last year and dramatically improved that in the Hydrus 2D in 3D, where we integrated all these editors into one single window, from where you can work with all these editors. And we have provided a list of all the various keywords, which are the words which drive the FreakC. And so you can simply click here and transfer those keywords, so without introducing any spelling errors. And we have added also various types of templates, so you can simply edit the text rather than typing it directly, which again simplifies that quite dramatically. And we say in the Hydrus Studio you have access to all these variables which you define in FreakC. Okay, well, now I want to give more information about this module, CRide, which focuses on the transport of particles and particle-facilitated solute transport. This module we developed only last year. We were contacted by Syngenta company, and they want to use some of these technologies to deliver nutrients and pesticides. And so, well, it is well known that many contaminants are relatively immobile, such as these radionuclides. They have retardation factors which goes into thousands, but they are immobile because they are strongly sorbed to soil. But they can also sorb not only to the soil or solid particle, but they can also sorb to colloids, which often move faster than non-sorbing tracers. And evidence exists that a lot of contaminants, such as heavy metals, radionuclides, and so on, are transported not only dissolved in water, but also sorbed to these moving colloids. And examples are listed here, so it's mostly heavy metals, radionuclides, but it certainly applies also to pharmaceutical oils and other contaminants. So we have developed this CRide module, which uses Hydrus as a driving force. In addition to that, there is a particle transport, which actually standard Hydrus can do as well. And I call particle transport, I call all the substances which have certain size, such as colloids, bacteria, viruses, nanoparticles, etc. And so this module, the specialty of this module is this particle-facilitated solute transport. So this schematic shows the main reactions involved in the transport of particles, so reactions such as attachment, detachment, which is a chemical reaction, or straining, which is a physical reaction. And then this slide shows the main reactions for the transport of contaminants in the presence of colloids. And so you see the sorption, either kinetic or instantaneous, but you also see sorption to these mobile particles. And each arrow here is represented by either ordinary differential equation or algebraic equation. And so all these equations have to be solved simultaneously. Bacteria acting as carriers for heavy metals is one of the specialized examples, or special examples, of the colloid-facilitated transport. And what's important here is that bacteria are relatively large. They're much larger than colloids, right? They're 10 times at least larger than colloids. So they are excluded from small pores. So especially in the saturated aquifers, they move mainly in the larger pores. And so they move much faster even than tracers or than water itself. And so they provide then a vehicle for rapid transport of these contaminants. I will not show any equations. I just show the simple verifications that we did for this. So this slide shows the breakthrough curves for colloids, which are the black lines, solute sorbed to colloids, which are the blue lines, and then for dissolved solute, which is the red line. And the retardation factor for colloid is equal to 1, and for solute is 4, so that means that it moves 4 times slower than colloids. And I showed the breakthrough curves for 2 scenarios. On the left, we applied colloids and solute independently to the column, and on the right they were solute was initially already attached to colloids. And so here you see the breakthrough curves are for colloids and here for solute. And so you can indeed see that the solute would arrive 4 times later than colloids, but you will see also a small fraction of solute arriving already together with colloids and at a much earlier time than you would predict using traditional models. And that's due to the sorption to these moving colloids. On the right here, the colloids and solute arrive at the same time, and that's because initially solute was sorbed to colloids, but you can see that solute is a smaller concentration than colloids, and that's because some of that solute is sorbed during the transport process, and that comes at later time retarded due to sorption. Okay, another module is a dual pair module, which focuses on preferential flow and solute transport. And preferential flow is one of the most frustrating processes, which really hampers our ability to make predictions of solute transport. And unfortunately, rather than being an exception, it's a very common phenomena. And here I show several natural environments in which preferential flow occurs, fractured rock, macroporous soils, or various heterogeneous sediments. And so for that we develop a suite of models, and you have seen application of some of these models yesterday. So we have a suite of models starting from uniform flow model, mobile, dual porosity, and dual permeability. This was all available in Hydrus 1D already, I believe, for already like 5 years. But this last one was not available in 2D. And last year I got some funding to develop this module and implement it into Hydrus 2D from University of Calgary in Alberta, Canada. These are the chemical non-equilibrium models which are available in Hydrus. The first 3 are the kinetic non-equilibrium models, and the last 2 combine both the physical and chemical non-equilibrium. So this is chemical non-equilibrium included into mobile model or dual porosity model, and here in the dual permeability model. And this is how Hydrus users see that. So these are 2 dialogues where Hydrus users can make the selections of these models. So here are these various dual porosity, dual permeability models. So the physical non-equilibrium model for water flow, and here it's then the combination with the chemical non-equilibrium model for solute transport. Yeah, here again I show one simple application of that, so for infiltration, basically bonded infiltration into the dew permeability system. So this slide shows the pressure heads in the matrix, so very slow movement at the moisture front. And then the next three slides shows the moisture fronts in the fracture domain for different anisotropy, different combinations of anisotropy tensors. So here is the faster in the vertical direction. No, this one is faster in the direction. Vertical direction, this one is faster in the horizontal direction, and this one is isotropic. Well, all these models are described obviously in the manuals at 1D, and in the specialized manual for the dew module at Hydrus 2D, and they are also all described in this paper. Okay, well, there is obviously these models have a lot of parameters, and people always ask me how to select them, and I always direct them either to these two papers or to the papers of Radka Korešova, who have a lot of experience with that, much more than me actually, how to get the parameters. Okay, another module is the Untitled module. And this module simulates carbon dioxide transport and production and major ion chemistry. Again, this module was in Hydrus 1D for quite a while. It was actually developed quite a long time ago, but I think in 2005 we put it into Hydrus 1D, and last year or 2 years ago we put it also in Hydrus 2D. This is the chemical system which this model considers. So these are major ions. Obviously there is no aluminium. And there is a lot of environmental or agricultural application for that. I have only one slide, so Diego, don't worry, I will give more about this. I think you have a presentation on this topic. So this just shows the application of unsubcant lysimeter study in which water contents were measured, sodium, electric conductivity, SAR, etc. So Tiago Ramos will give a presentation later today on this. And now we have it also in 2D, and it's fully supported by the graphical user interface with all the variables with the possibility to display all these various exchangeable species, solid species, liquid species. Wetland module, I don't think I have anything except I left this slide there, so you can see the vertical flow wetlands and horizontal flow wetlands, which Ginter said that he didn't have this slide or something.
No, I deleted it.
Or deleted it, so I didn't. Okay, the final module which I developed in the project for California EPA was the Fumigant. Fumigants are chemicals which are used to sterilize the soil. They are highly volatile, so they are mostly in the gas phase. So the main transport mechanism is the diffusion in the gas phase. And yeah, so this specialized module deals with some special management technologies really of applications of these fumigants, such as presence or absence of surface tarps, because they always place the surface tarps to prevent these fumigants from going into the atmosphere, because some of them are endangering the ozone layer. And then this tarp can have certain temperature dependence. Tarp is removed at certain time, etc. So that's a specialized module. We just recently had a paper in which we did sensitivity analysis of various parameters for different technologies of applying these fumigants. When I have this, I would like to mention one thing, that if you see sudden changes in fluxes of volatile chemicals as well as gases, then it's not necessarily numerical oscillation. These fluxes can change quite dramatically for various reasons. This is just effect of temperature. But there are much more important factors such as irrigation will basically stop those fluxes right away because it will close the pathway through which the fumigants can leave. And I had the paper on this in 1992 where I show how quick these fluxes can change. And so taking a measurement like once a week doesn't give you any information. Okay, so that was about the modules, and then now some new features which we put in the Hydrus code. So last year we released version 2, and in that version 2, so these are some of the features in version 2. We started supporting completely three-dimensional geometries, and we also allowed a specification of various properties on geometrical objects, etc. I have actually slides on each of these. So until last year we supported only geometries up to here, something like that. So you could have either simple or general 2D geometries, and then you could have either simple or we called it layered geometries in 3D, which basically meant that you could have a general 2D geometry as a base from which you could build up the model in the third dimension. So last year we released a version which we call 3D General or 3D Professional, and in which you can develop practically any types of three-dimensional geometries. To be able to do this, so we have to introduce some new additional objects by which you can define these geometries. So in addition to planar surfaces, we also have curved surfaces, and here's the list of these. So these B-splines and quadrangles are the surfaces which are mostly used to define complex 3D geometries, but you can also have some pipes and rotary surfaces, etc. And here's an example of three-dimensional geometries. The first one defined simply using planar surfaces, the second one using these curved surfaces, pipes, etc. And you can define very, very general geometries. You can have the disappearing layers, etc. You can have very complex drainage system. And you can also import complex geometries from DXF, TIN, and STL software, and these are some of the tests that we did. And about 10 years ago, I did actually have a project where I was doing simulations of flow in the giant Buddha statue. And at that time, we had to assume that Buddha is axisymmetrical, but now we could simulate. In the previous versions, you had to define properties and boundary conditions, etc., directly on the finite element mesh. And if you had to redesign the mesh, you had to you would lose all that information. So now in the new version, also you can define properties on the geo objects, which are independent of the mesh. And if you need to redefine the mesh, let's say because of some problem with the stability of the solution, or even if you have to change slightly the geometry, so you don't lose all that information, and it is preserved. There is a three-dimensional version of the Hydrus predecessor SWMS3D, which is called PowerSwim, that was developed by Forschung Centrum in Jülich based on our earlier code SWMS3D. And it's meant for supercomputers or clusters of computers. It was tested on a large number of processors, and they showed that if you increase the number of processors, let's say 1,000 times, the simulations run 1,000 times faster. So we fully support this code now, so we can develop that in Hydrus, export input data to supercomputer, and then import it back. We are pretty close to finishing also development of our own parallelized code, which will be meant not for supercomputers, but will be meant for computers with multi-core processors, right? Which is where the development is going now. I think you can get 8 or 16 cores on the computer right now. So that you can have different types of outputs which were not available. Also, we changed the licensing system, so now users can control their license themselves online. We also have added, we always had complaints for some reason that we display only some standard variables, and I thought usually that's enough if I show concentration in the liquid phase because you can calculate all the other from that. But on the request of many users, we added a lot of so-called alternative or derived variables. So you can display salt concentration, gas concentration, total concentration, so different variants of it. Also for mod flow people, we added not only pressure, but total pressure and so on. Okay, and then we added several other simple options, such as initial condition doesn't have to be specified in the liquid phase concentration, can be specified in total solute mass. That's important if you do the inverse problem, because if you optimize for KD and you have initial condition in terms of liquid phase concentration, so obviously you are changing mass during every run. And so now you can specify the total mass, and the code will redistribute that between different phases, even if you change KD, KH, etc. Yeah, we also have included a lot of different types of boundary conditions, and here I list only some of them. So some are quite specialized for the irrigation purposes. So for example, we have subsurface drip boundary conditions where the flux of the dripper accounts for the back pressure, so that was developed together with Naphtali over there. We have surface drip boundary conditions that the wetting area is dynamic, and so on. We also have an option for the trigger irrigation that you can specify, maybe it's here. You can select an observation node, select triggering pressure, and once this pressure is applied, it's then applied to selected variables which you can select. You can select information rate, irrigation, duration, etc. And here's an example from the application that was just published, and I don't know if nobody is talking about it, so I'm not talking about it. I'll just save my time. What was that? Yeah, and then there are some other things. Yeah, both models now implement this fully compensated root water and solute or nutrient uptake, which we developed in this paper with Jan Hockmans. And the nutrient uptake is divided into passive and active, and you can turn off passive or turn off active and turn it on and off. And so users have a lot of flexibility in defining their uptake functions. Suddenly the program became, with the release of the second version, about 3 times faster by some improvement in the coding and so on. We are working on some other modules. Some of them are already available, but since they are not particularly robust, so we didn't include them in standard version. But we simply put them on the website and people can download them. So there is an overland flow module, and I will be returning to it this year and trying to make it more robust, because we have a project for the overland flow of particles, of bacteria or pathogens, and so we need to make it better than it is. There is a freezing module which is for 1D, which is available online again. We are planning to work also on the stability problems. With Jasper group, we are always discussing implementing these global optimization techniques, but we'll see how that goes. flow module which we currently have. So basically we describe the overall flow using kinematic equation. It's linked with the atmospheric boundary condition, and then the overall flow can redistribute water over the surface. And finally, well, last year or 2 years ago we published this book, Hydrus textbook, so let me make some advertisement here also. It's called Solve Physics with Hydrus in Modeling and Applications, and we try to explain different processes in the Vedas of hydrology using the Hydrus code. It was written by David Radcliffe mainly. That's all I have, so I got finished before the clock. So if you have any questions.
So thank you, Jirka. If there are any questions or suggestions for improvement, you can ask me.
Wish list. I was planning to put there also a wish list, and it would be to Mirek, who is not here, so I can say, stop changing those damn icons.
Yes. I have some suggestions about the improvement of warnings, or if the user selected a coarse grid for the finite element, Hydrus can suggest refining the grid to get better. If he selected clay with a model, a soil model which is not suitable, it should suggest changing this. This is not suitable with this, and many other improvements. If the mass balance, is huge, it should stop and suggest refining or whatever.
You see, people usually think that if the program crashes, that's the disadvantage, and that's actually the advantage, because it doesn't give you the wrong answer. It crashes. It rather crashes than giving you the wrong answer.
But it can warn us before crashing to improve.
Yeah, well, it's very difficult to do that, right? Because Richard's equation is highly nonlinear equation, and so how fine the grid should be depends on so many factors that I try to write some kind of guidelines, which I posted online. I think it's called Notes on Spatial and Temporal Discretization. Because discretization depends very much on first of all, on how nonlinear these hydraulic properties are, right? And different obviously soils or properties at different soils are differently nonlinear. So then the different soils require different discretization. For example, loam, which we were using in the course, is the least nonlinear, and so Hydrus works almost on any mesh for loam. The most nonlinear soils are, on the other hand, the coarse textured soils, which are gravel or sands, and for that you need very fine discretization. But then again, it depends also on the boundary conditions, right? Because if you have ponding infiltration, so the fronts are very sharp, right, in the sand or gravel. And then to be able to describe these fronts, you need several nodes to be able to describe them. So if the front is 5 centimeters, you need several nodes to be able to describe that. If you have long, and then the front is ½ meter long, then you need the same number of nodes for that. So it depends from the nonlinearity of the soils, it depends on the boundary conditions, because obviously ponding is the worst boundary conditions. You have fluxes, small, like daily values of fluxes, then you don't need fine discretization. Yeah? If you then specify 15-minute fluxes, then you need much finer discretization. So there is so many factors that it's difficult to just put in the code some artificial intelligence.
It can be put in a smart help.
Yeah, smart.
Smart help. Yes, like the programs of Microsoft.
The problem is that the day has 24 hours, you see.
But the mass balance can be something. If you can show the mass balance, but mass balance is hidden somewhere in the.
Well, mass balance is obviously reported there.
Yeah, but if it can allow that the mass balance is not,
and that's,
I don't know,
that's
maybe set a threshold of 1%. Then
that's the first thing I'm always looking at, right? Whether the mass balance is okay.
If
and if the mass balance is okay for water flow, then the solution is likely correct, because at that nonlinearity, if the code finds a solution and the mass balance is okay, then there is a very high likelihood that the solution is okay. And obviously, how fine the grid should be also if you have these, like you said, right, several orders of magnitude differences in conductivity. Yeah, these techniques are not really good for that. It's so obvious.
Okay.
Yeah. Okay. Any other question? Okay. Thank you, Jirka. Then we go to the next presentation right after.